change gears now and begin to talk about the effects of inelastic scattering of electrons. And that gives us additional information for characterizing our materials. Again, I apologize for the voice. Hopefully it'll be a little bit better tomorrow. So far, we've looked at the microscope as a tool for generating a beam, creating images, creating diffraction. That's a valuable bit of information. You saw some beautiful images of defects that Hamish was showing you today. Here's another nice image of defects in a material. Now, can we do diffraction contrasts on these and analyze what's going on? Yes. Can we do morphological studies on this and say, well, what do I have? I've got rectangular things, round things, square things, all kinds of stuff. We can spend a lot of time doing the defect analysis, and that'll be valuable information. But is there another way that we can get information? What if I could go up to this, and this is an engine aircraft alloy, aluminum alloy. What if I can go up to that, and if the question is, we've added alloying elements, can the diffraction contrast experiments tell us where those alloying elements are? Not very easily. However, if we use inelastic scattering spectroscopy on that same area, that image becomes that image. All right, now I have a whole new wealth of information about the solid. I can tell you where the manganese is, where the magnesium is, where the zirconium is, and very importantly, these little tiny blue dots where the europium alloy additions are gone. How do we get that? That's going to be what we're going to talk a little bit about today and finish up more tomorrow. And hopefully I can talk a little better. Okay, we're going to do this by doing inelastic spectroscopy. We're going to take the beam, interact it with the sample, and measure additional signals that come from that solid. Okay, we're going to do two kinds of spectroscopies. I'm going to first talk about X-ray energy dispersive spectroscopy, and then by electron loss spectroscopy. Right now, you have EDS spectroscopy on the machine. And correct me if I'm wrong, or not wrong, you're getting an EEL system. Yep. Okay. Okay. Why do we want to do EDS spectroscopy in a TEM? First question. Most of you probably know you have an SEM. You probably have an SEM here. Sorry. And I'm sure it probably has an EDS system on it. And you know you can put the probe on an area, measure a spectrum, and get some elemental information. What's the limit of that? The limit of doing that analysis is the fact the probe comes in and interacts with the solid, and there's multiple scattering going on, and you have an excited volume. In an SEM, on a good day with the wind blowing right, on the right phase of the moon, you might have a spatial volume of a micron or two. Okay. Can we adjust this? Yes. We can make that volume smaller by adjusting not the size of the beam, but the energy of the beam. All right. Is there a way we can increase the resolution? Well, what's the limiting factor here? This. How do we get rid of that? Chop. Cut it, make it smaller, and make it smaller. So we increase our spatial resolution. At the same time, from the SEM to the AEM, or now the TEM with a probe corrector, that probe size gets smaller and smaller. So we can change our analysis volume from microns down to sub-nanometer volumes. And with the phase of the moon right and the right sample, the perfect sample, we can even get down to atomic levels. All right. A couple other examples of that. You've seen some of these examples before. This is the catalyst particle that I showed you early on. Was it yesterday? Yesterday. So the colors have changed. All right, so the whole point is we can get a huge amount of information from elastic scattering, but not everything. In this case, we can see the precipitates. In this case, can we see the catalysts? The answer is no. In this case, we can augment the image information by the chemical information. In this case, we need the chemical information to localize where the catalyst particles are. Okay? And for those of you, and how good of a scale, this is a micron scale. That's a 20 nanometer scale. Those of you with really good eyes can see at some point we're actually looking at single atoms of ruthenium. There's another example of that. An engineered material. How many of you have heard of something called atomic layer deposition? It's a methodology of laying down literally monolayers of material. Okay? This was a fabricated test sample, and we put down 1 monolayer, 2, 4, 6, 8 monolayers on top of silicon. So we got silicon, aluminum oxide. Then I put a monolayer, first of manganese oxide, then titanium oxide, and then 2, 4, 6. Look at the image. In the image by itself, it's very difficult to say where something is. I can say for sure there's something here. Can you see anything here? On the other hand, this is a very quick, fast scan. Oops, the color changed. It's supposed to be blue. That's supposed to be blue. I guess it's blue on there. We can see, even with 1 millisecond per pixel, I could say there's a monolayer of manganese oxide there and titanium oxide. And look very closely, you can actually see the offset because one is added after the other. So what are we going to talk about a little bit today and finish up tomorrow is we're going to first talk about X-ray generation in the microscope, then about the detectors, a little bit about the instrumentation. Data analysis and quantification is essential to understand this, and then we'll talk about a few other things that add to that. Okay, how do we employ inelastic scattering to get a signal? In the electron microscope, elastic scattering is the beam comes in and goes straight through with no energy loss. In inelastic scattering, the incident electron beam comes in, interacts with the inner shells of the atoms, and can either, if it interacts with one of the inner shells, it can eject an inner shell, and it can lose energy. That process is electron energy loss spectroscopy. Okay? When that happens, after this event, we now have a vacancy in the inner shell. The atoms don't like to be excited. Hamish doesn't like to be excited, right? He likes to be calm. Okay? I don't like to be excited, or at least I like to talk. Don't like to talk excited. What's going to happen is the electron energy population is going to redistribute itself. And the electrons from a higher order shell are going to drop down to fill vacancy and release energy. When it releases energy, that atom is going to come by and give off something, give off radiation. It can either emit a photon, in this case an X-ray photon, or it can emit another electron, an Auger electron. Okay? These are competing processes. You either get, if you have electron energy loss and you've excited an inner shell, you either get an EDS signal or an Auger electron. Okay? The spectra from these three different spectroscopies looks completely different. In electron loss spectroscopy, which is we'll talk a bit tomorrow about, we have energies that have lost electrons that have lost no energy, and then electrons that have lost different amounts of energies. We'll talk more in detail about this. In EDS spectroscopy, what we have are nice characteristic peaks. Those peaks are fingerprints. We'll tell you that bit in a moment. The two spectroscopies are complementary, and they look to be completely different. They give us different information. Okay? Where does the information come from? If we've had our incident electron come in, and we've knocked out an inner shell electron, and that primary electron now has lost some energy, we can measure that. But what's happened is this electron's lost energy because, the primary electron's lost energy because it's knocked the electron up to an inner shell. And usually it'll knock it above the Fermi level. So this electron will probe information above the electric scattering above the Fermi level. When we get an X-ray emission photon, what's happened is that electron's now jumped out and another electron drops down. What we're going to get there is information about the distribution of electrons from that state to that state. You could see that in the shape of the spectrum. Okay, let's first look at energy loss spectroscopy. So we've knocked an electron up. That electron cannot go into the filled atomic states. It has to go into a state above the Fermi level. So the electron spectroscopy is going to reflect the density of states of matter above the Fermi level. Okay. If instead, okay, so if we look at, oops, wrong guy, forward. So here's an electron loss spectrum from copper. This is copper, this is copper, this is copper, all copper. Here we're looking at the electrons come in, it's not electrons out. When we look at information about the empty density of states above the Fermi level. X-ray photoelectron spectroscopy, on the other hand, is a different process. In X-ray photoelectron spectroscopy, we're knocking photons come in, we're knocking electrons out, but we're looking at the energy distribution of these. So energy loss spectroscopy probes the empty density of states. X-ray photoelectron spectroscopy probes the full density of states. Oops, I keep hitting the wrong button. All right, so here's copper. We're probing the empty density of states. Here's X-ray photoelectron spectroscopy. It's the full density of states. They're complementary to each other. Okay? And X-ray energy dispersive spectroscopy, on the other hand, doesn't probe that. It probes the transition between state A and then between the initial state and the final state, and that's simply an energy difference. Okay. Forward. When we knock an electron out of a shell and another electron from a higher shell falls down, there's a very specific energy difference between those shells. Okay? If we knock an electron out of a K shell, electrons from higher order shells can drop down. If it goes from an L shell to a K shell, that's an alpha line. If it goes from an M shell to a K shell, it's a beta line or a gamma line. If we knock the initial state out of the L, then we can get an L alpha, L beta, L gamma. Again, it's just a simple transitions. The energies of X-rays change with atomic number. Okay, as we go up in atomic number, the energy of those lines gets higher and higher. So that's a characteristic thing. The other thing that's very characteristic is the energy difference between these states. The energy difference between these states is the difference between the initial and the final states. So that's you all know that when you study from your physics courses and chemistry courses, the shells have very discrete energy levels. So we know these energy differences are very discrete. They're a fingerprint of what's in your solid. One other thing to know about the lines, the transition probabilities, the relative intensities of lines is also very characteristic. Alpha lines are always the most intense because they're dropping the shortest distance, followed by beta lines, followed by gammas and etas. Okay? Generally, so these are all normalized at the most intense is 100. So the alpha lines are the highest, then come the betas, and I've given you a range here because it varies slightly with atomic number. Same thing holds for the L's and the M's. There's an example of a specimen. It's a semiconductor, yttrium barium copper oxide. So I picked this example because it shows a nice example of everything. First of all, we have the copper K line, the copper K alpha, and the copper K beta. Look roughly at that ratio. It's about 1 to 10, which was similar to that. So 1 to roughly 10. Okay. Oops, forward. So we got the copper K. If we have a copper K, we also have a copper L. Copper L here's a little more complex. We'll talk about that later. The other thing is we got a yttrium K. Now, higher atomic number, higher energy. We still have that ratio, roughly 10 to 1. Okay? Barium's a much higher atomic number. Okay? In barium, we're going to be looking at the L shell intensities. Why? Because barium's up here. We're going to be looking at the L's because I want something in this energy range. There is a barium K. It's up here somewhere at a much higher energy. Okay? And that we don't see in, we don't see in the spectrum. It only goes to 20 kV. You can measure spectra at much higher energies. Most people tend to work in the range from 0 to 20. Occasionally they'll go to 40. It's very rare for somebody to go higher. Oh. One last thing. If you have a K line, you will always have an L. If you have and if possible, an M. Okay. Why is that? Because the energy of the beam we're using in our microscope is sufficiently high that it'll ionize things. Remember, with 10, most of you will probably be running at least 100 kilovolt energies. Some will be running at 300 kilovolts. At 300 kilovolts, you'll excite the entire periodic table. You may not detect it because the lines may be way out here, or you may be looking at very high family lines, L's, M's, N's. In addition to characteristic energies, we see a spectrum rides on top of a background. That background is also due to an inelastic scattering process. It's the incident electron interacting not with the inner core electrons, but the nucleus. It's called Bremsstrahlung, breaking radiation in German. Okay? And it's due to the electron beam coming down, interacting with the nucleus. This Bremsstrahlung radiation is the same thing that's generated in the synchrotron when the electron beam goes around. Okay? That background shape is very characteristic. And I want you to remember this, because when you're in a lab, because looking at the background, you can tell if everything's working right or not. So first of all, that background will be a continuously decreasing intensity. It'll stop at the energy of the electron beam. Okay, if you're on a 300 kV electron beam, you'll never get there. But if you're on an SEM, you'll see that point. It'll continuously rise as we go down in energy, but in the real world, we never see it going up continuously. Here's an example of an experimental spectrum from beryllium. Okay, it starts out low, starts coming up, and then drops off. It's dropping off here because their detector is inefficient down there. Again, we'll talk about that. Okay, the shape of that background goes roughly as 1 over the energy, and actually goes as the energy difference, incident beam minus the energy you're looking at, divided by the energy, times the atomic number. Okay, so what does that tell you? The background is atomic number dependent. Okay, so higher Z materials also have higher background. Lower Z materials have lower background. And there's always a cutoff. Here's that other spectrum we were looking at just a moment ago, but I've just blown it up a little bit. So we can see that continuously decreasing background. Okay, we can see it's doing something funny here. Why didn't it drop all the way down? There's too much other information here that we can't see it. Okay, but you can see it's starting to drop off. The other important thing on this background, I want you to remember this, that background should be, after we get that initial dump, should be going down continuously. Okay, you can use that. Here's the background. Now this is a log scale now. As a function of energy. You notice I'm going very high in energy now. And it's going down continuously. That's great. Look at this background. It's not going down continuously. There's something strange going on here. What's happening is there's a fault in the system, and we're actually getting electrons into our X-ray detector. So if you see the background and it's not dropping off, you know you've got a problem with the system, and you need to investigate that to make sure we're okay. Okay, I'm going to spend just a few more minutes talking about the different detectors, and then we're going to stop for today. All right, there are a whole slew of different kinds of detectors. There's wavelength dispersive spectrometers, energy dispersive spectrometers, and there's 2 types that you will generally see. The lithium drifted silicon detectors, if you're an older system, or the newer ones, the silicon drift detectors. We're not going to talk about these guys. We're not going to talk about the germanium detectors. I don't believe any of you will ever buy one of these. These are about $500,000 a piece. These are usually high energy physics. We'll talk a bit about some of that data. So I'll mention wavelength dispersive spectrometers because it's a traditional detector, and they operate very simply. We can recognize them very easily by looking at an instrument. Okay, here's an SEM, here's a TEM. The lithium drifted silicon detectors can be recognized very easily by the large dewar that's on the side of the microscope. That dewar is generally filled with liquid nitrogen. Okay, so there's one there, and there's one there. In the newer STD detectors, that dewar is gone. We'll talk about that. Wavelength dispersive detectors are huge monsters. Okay, they're mechanical devices. You rarely see them on TEMs. Okay, can it be done? Yes. Is it done traditionally? No. So all of the energy dispersive spectrometers, whether it's a SILI detector or an STD, work on the same principle. Okay, there is a specimen. It hits by an electron beam. X-rays come off. They hit the detector. We'll talk about that in a minute. A signal is generated, amplified, and a spectrum is produced. Was there a question back there? Or no, you're stretching. That's fine. I see a hand up. Wavelength dispersive spectrometers work on the principle of Bragg's law. Just like we talked about Bragg's law for scanning with electrons, you can get Bragg's law for scattering of X-rays. Again, the same principle. Electron comes in, X-rays come off. This time they hit a crystal of known spacing. They diffract off, and the detector measures those. Okay, this is rarely used in a TEM today. The reason is these are generally large devices. They're complex mechanical devices. They have excellent resolution, but they're complex devices. The focus is dependent on height. They have limited solid angles, and they're serial detection. So generally, you won't be using those. Oh, and I'm sorry, did I skip some? I skipped the slide. Yeah, the nice thing about EDS detectors is they're simple. They're nearly operator independent, not quite, but nearly. They can have very large solid angles. That's an important factor for today. They're virtually specimen position independent. There's almost no moving parts. And they have nearly parallel detection capabilities. The downside is they have poor energy resolution. They have mediocre peak to background ratios, and the detection efficiency depends on the energy of the X-ray. All right, I'm not going to spend any time talking about the wavelength dispersive in the TEM. That's the modern one. This is the point I want to make about a comparison between an EDS spectrum and a WDS spectrum. Same material, two different detectors. This is EDS, this is WDS. Again, same thing here. EDS in a line, solid in WDS. You see the huge difference in energy resolution. Okay? Well, you say, well, that doesn't matter. I can still tell there's chromium there. I can tell there's iron there. Absolutely true. But what about something like a barium titanate material? The barium L and the titanium K almost completely overlap. Not quite, but almost. In an EDS spectrum, you don't have the resolution to resolve that. In a WD spectrum, you can resolve that. Okay? Is there another solution? Yes, eels, but that'll be tomorrow. So we won't spend any more time about this. I already described it. We're mainly going to be talking about EDS type spectrometers. Again, I told you can recognize EDS spectrometers very easily. On the column of a microscope, you usually have a large dewar that can do two things. One, it can be a cold trap to cool down the cold finger in a microscope, but they're just also used in a lithium drifted silicon detector to cool the detector down. Today, SILI detectors are getting fewer and fewer. Okay, everybody's changing to the STD or silicon drift detector. These devices don't need cooling, but they don't need liquid nitrogen cooling. They operate at about minus 30 degrees C. That can be done with a Peltier cooler. What's good about that is Peltier cooler has no moving parts. You don't have to continuously refill liquid nitrogen. You don't have to remember it. And they're very rapidly cooled and warmed up. With a lithium drifted silicon detector with all the nitrogen, if you need to warm up the detector, you got to dump the nitrogen. You got to wait for everything cool. Takes a long time. And if somebody vents the column, what's going to happen? You got a thing full of liquid a cold finger of liquid nitrogen, you vent the column. What's going to happen in a day like today and the humidity inside? You're going to get water vapor condensed around the cold surface. So it's not a great idea. In an STD, they warm up very quickly. You won't get, you unlikely will get water there. You can, but you may not. All the detectors are very similar. Recognize this one? This was the first X-ray detector I ever put on a column of microscope at Illinois. We had to design everything back then. We bought the detector, but there was nothing else available. Okay, the detectors, I don't care which one it is, are usually enclosed in some kind of environmental housing. Why? Because the front of the detector is usually cooled. Even if it's an STD, it's cooled still. We have an environmental housing that surrounds the actual detector. This is a lithium drifted silicon detector. It's literally a piece of silicon. I'll show you a picture of that in a minute. Behind it is a field effect transistor. The X-rays come in, they end up in the crystal. X-ray signal is generated. The reason for cooling these to liquid nitrogen is to reduce the noise in the FET. And you'll see why in a minute. On the front of a lot of these detectors is some sort of environmental protection window in case you dump the column. Okay, you really don't want it. Back when I first started, this is actually a picture of the front of that one of these. They had beryllium windows on the front, typically about 8 microns thick. Nowadays we have different kinds of windows, or we can actually run windowless. The way we make a silly detector is we take intrinsic silicon, we diffuse lithium in it under reverse bias. We segregate it, get an intrinsic zone. We take that crystal, we chop off the front and the back, and now we've got a piece of intrinsic silicon with a P and N on either side. Think of this as a capacitor. Okay? How do we get signal? Well, see, I think that's the next slide. No, let me go a little bit further. The STDs are, again, slightly different. They're a very small chip. The difference here is in the lithium drifted silicon detectors, these guys are typically 3 or 4 millimeters thick. In an STD, it's a very thin silicon chip, about 0.3 or 0.4 millimeters thick. It's intrinsic silicon. It sits on top of a Peltier cooler. The nice thing about these things is the Peltier cooler cools them, and they're very small. They can be fabricated in lots of different shapes and sizes. You can have round ones, rectangular ones, different shaped ones. You have a Super X system, right? That's a detector. This is what the detector for a Super X looks. That's actually a detector from a Super X detector. I take things apart. I think Hamish will vouch for that. All right, the STD is, again, very thin. What happens in the STD, rather than having one big big capacitor, what happens is we have a back contact. The X-rays come in. They dump energy into the silicon. When it dumps energy into the silicon, it creates electron hole pairs. On the other side of the silicon, not the side that the X-rays come in, but the back side, there's a set of voltage rings. We set up a voltage ramp across the back of that, and the electron hole pairs get attracted to that voltage ramp, and they travel up this to the anode. What do we see when an X-ray comes in? A burst of electron hole pairs gets generated, and a small bit of charge comes up here, and we get a voltage pulse. I think that's my next slide. Yes. And I think one or two more slides, and then we're going to stop. All right. So what happens? How do both the silly and the STDs work on the same principle? We've got a piece of silicon here or here. An X-ray comes in and creates electron hole pairs by N-ionizing. Now, in silicon, it takes 3.8 eV to create one electron hole pair. Okay? That's characteristic for silicon. So if you have a 10 kV X-ray, it'll generate 2,630 electrons, or 4 times 10 to the minus 16 coulombs. Very specific. So what do we want to know? How do I know the energy of my X-ray? All I have to do is measure the charge that's built up here. So X-ray comes in, creates so many electron hole pairs. I measure the charge. I know what the energy of the X-ray is. That's how the detectors work. What's typically done is that X-ray comes in, the charge gets built up, and then we use some sort of a measuring device to measure how much charge. In these silly detectors, there's the FET. It's cooled down because that's a pretty small charge. And kind of electronic noise disrupts it. So you cool it down to make the FET more efficient. And the same thing here, you cool them down. It doesn't have to be as much. So an X-ray comes in, what happens? We get a small charge pulse or voltage pulse. The height of that pulse is directly proportional to the energy of the X-ray. Another pulse comes in and jumps up. Another pulse comes in and jumps up. Between pulses, what we do is we want to measure the voltage jump. We want to know that height. That tells us what the energy of the X-ray is. So your system is actually just a series of steps. Okay, and we're measuring pulse heights. We have a pulse height analyzer. That's what an X-ray analyzer is. It's a pulse height analyzer. It's measuring these. It's measuring the pulse height over a series of time. The longer the time we take to do the measurement, the more accurate we know the energy. Okay. And after a certain amount of time, we have to reset everything because it's a capacitor. You got to discharge it. Okay. That's how the system works. Let's see, what's the next slide? Okay, so the X-rays come in. There's actually, let's finish. Two more slides and then we're done. So the X-rays come in, they enter the crystal, and we get pulses coming out. How good is the detector? Well, the detector is only as good as the ability to get that X-ray into that point. I already told you some detectors have a window in front. I also already told you that these things are semiconductor devices. There's electrical contacts on the other side. All of those stop the X-rays from actually getting into the region that I want. Okay? So there's an intrinsic energy barrier to getting those X-rays in. Okay? And that's a simple absorption effect. You all know X-ray absorption. An X-ray goes through a material. It gets decreased exponentially according to whatever the material is and the thickness of that material. So it's an exponential decrease. The higher the energy, the easier it is to get in. Okay? So this is what a typical efficiency curve for X-ray energy is. And now I'm down at the low energy end. Very low energy X-rays can't get through the window. So the energy drops off, the efficiency drops off to zero. Remember the background curve I showed you? It came up and then dropped down. It's dropping down because of this effect. If I change that window, if I go from a beryllium window to a polynomial window to no window, that efficiency gets better. Great. Why doesn't it go to 100%? Well, it still has to get through into the silicon. So at a certain point, you can't get any better than this. As the energy gets higher, it's easier for the X-rays to get through. It goes up to near 100%. Okay? But there is a problem. If the energy is too high, what's going to happen? The X-ray is going to go right through. And so what will happen is at the high end, the efficiency, so this part is this part. This part is the high energy end. And if the X-ray energies are too high, it'll go near 100%. And then they'll start going through the crystal, actually right through into the back. Think of all the lead shielding you have on your microscopes. The high energy X-rays are generated. They're going to go right through the crystal. And this intensity is going to drop off. Depending on the thickness of your crystal, your high energy efficiency is going to be either good for really thick crystal and gets worse for thinner crystals. The old silly detectors at 3 millimeters thick were near 100% out to 20 keV. The new STDs tend to be around 0.3 millimeters. So they start dropping off about 10 keV, and by the time you hit 20 keV, they've lost a lot of efficiency. Doesn't mean they're not working. No, they still work. We just have to realize that. Why am I going through this? It's important to understand this curve when we ultimately try to quantify data. Okay, we're going to stop there. No, one last thing. And I already told you about changing the window. Changing the window increases the efficiency. I'll just show you. This will be the last slide. Yeah, I think it is. Yeah, last. So the very dark curve is a beryllium window detector. We see the nickel K, high energy X-rays, 100%. We see the nickel L. But do we see, this was a nickel oxide sample. Do we see oxygen? No, because the efficiency's gone down. If I remove the window and go to a Windows detector, not only does the efficiency for nickel L increase, more efficient, but we're also starting to see low Z elements. All right, here's a more modern detector. This is my new detector on my machine. Not only, and now I'm going to go down very low in energy down here. Not only can we see oxygen, carbon, I can go all the way down to beryllium. Okay, so in a modern machine, you can do almost the entire periodic table. You can go from beryllium. I've gone from beryllium to uranium. Now, you can't do hydrogen and helium. Anybody want to tell me why? Okay, hint. In order to get an X-ray, you have to have electrons in a shell above. Hydrogen and helium only have a K shell. Only the first shell, one S shell. If you knock the electron out, there's no electron to drop down. Hydrogen and helium do not emit X-rays. So you can't do EDS analysis on hydrogen and helium. There are other techniques we can use. Okay, so when we come back tomorrow, we're going to talk about artifacts in spectra and go on from there. So let's call it a day, okay? Thank you.